and machine learning. In this lecture, we will briefly discuss about the topic Gaussian mixture model, that is GMM. All we should know that why we should learn this GMM, Gaussian mixture models. Learning Gaussian mixture models, GMM, is valuable for understanding probabilistic modeling, clustering, and density estimation, enabling applications in data analysis, image and speech recognition, and anomaly detection, and providing a foundation for more advanced machine learning techniques. We'll see one by one. So first, we should know what is Gaussian mixture model, that we are calling it as GMM. This Gaussian mixture model GMM is a probabilistic model used to represent normally distributed subpopulations within an overall population. Rather than assuming that all data points come from a single distribution, the GMM assumes the data is generated from a combination or a mixture of several Gaussian distributions. Each component in the mixture represents a different cluster or subgroup, allowing GMM to model more complex data patterns than single distributions. So we can represent the mathematically we can represent the GMM in terms of P of x is equal to summation k is equal to 1 to k pi k into this n represents the normal distribution of x given mu k comma summation of k, where this k represents the number of components and pi k is the mixing coefficients, that is varies from k is equal to 1 to k, pi k is equal to 1, and this normal distribution of x given k mu k comma summation of k is, we are calling it as a Gaussian PDF, that is Gaussian distribution with mean and a covariance matrix. We can say that. Next, Gaussian distribution is given by the formula. We can write it for 1D and also for 2D. The 1D Gaussian is written as, there is a normal distribution of x given mu comma sigma square is equal to 1 divided by root of 2 pi sigma square into e to the power x minus mu divided by 2 sigma square. This formula we should remember it for solving the problem. And in 2D Gaussian, this we can call it as elliptical, a normal distribution of x given mu comma summation is equal to 1 divided by 2 pi to the power t by 2 modulus of summation to the power 1 by 2 e to the power half x minus mu the transpose, here summation inverse x, that divided by summation x minus mu, or otherwise summation inverse we can write like this. So this formulation accounts for the direction and magnitude of spread using the covariance matrix, the summation of sigma, and it is particularly useful in modeling real world multivariate data. And GMM in action, that is mixture of Gaussians. The Gaussian mixture, the GMM models use the multiple Gaussian distribution to collectively model a data set that might not be well represented by single distribution. Each component Gaussian captures the data distribution of the specific subcluster, and their weighted combination forms a more flexible model. The use of multiple Gaussians allows GMM to fit complex data shapes and such as multiple peaks or overlapping clusters, which cannot be achieved with a simpler clustering algorithm like K-mean. See here, we are finding here various clusters. So this model will give us as the weighted sum of Gaussian. This is one Gaussian function, see bell-shaped function. This is the cluster 2, this is the cluster 3. So we are going to get the output of the weighted sum of all these clusters. We are going to get it in this GMM. And what are the parameters we are using? Each Gaussian component in a GMM is defined by 3 key parameters. The mean vector mu k, we can call it as mu k, the covariance matrix summation sigma k, that is summation k, the mixing coefficients pi k. The mean vector determines the center of the Gaussian. See here, This is the center of the mu. Represents what? Center of the Gaussian. And the covariance matrix describe the covariance matrix, what it will do, describes the spread and orientation. This covariant matrix spread and orientation, and the mixing coefficient defines the relative importance or weight of that Gaussian in that mixture. The overall goal of using GMM is to estimate these parameters so that the combined model best fits the observed data. Next, learning parameters using EM algorithm, that is, EM algorithm. This we are going to see it in the next lecture, even though I will be giving you a small introduction about this. The expectation maximization algorithm is an iterative method used to estimate the unknown parameters in the GMM. The algorithm alternates between two steps, expectation step, E step, and maximization, EM step. In the E step, the algorithm estimates the probability that each data point belongs to each of the Gaussian component. In the M step, what it will do is it updates the parameters of the each Gaussian using the probabilities computed in E step. This process continues iteratively until the model converges to a stable set of parameters. First, E-step responsibility calculation. This is the calculation for E-step. In the E-step, the EM algorithm, we compute the responsibility. We can call it as R, which is the probability that a given data point, this xi, belongs to the component under K. This is calculated using the Bayes theorem. See here, pi k into xi given mu k divided by pi j, that is summation pi j. So we are calculating using the Bayes theorem, and this gamma ik is the probability that point xi belongs to the component x. So the responsibility represents a soft assignment, meaning a data point can particularly belong to multiple clusters rather than being assigned to just one as in hot clustering. Next, M step update. Here the M step update, during the M step, the parameter of GMM are updated using the responsibilities computed in each step. The new mean, mu k, is the weighted average of data points where the weights are the responsibilities. Weights are the responsibilities. The covariance, this is the covariance matrix, is updated based on the spread of the data points around the new mean. Here x minus mu is the new mean, again weighted by the responsibilities, weighted by RIK, the responsibility. The new mixing coefficient pi k is the average responsibility, because here we are dividing by n. RIK is equal divided by n, average component of k across all data, reflecting its proportions in the data set. These updates, so here we can write like this. Next, log-like likelihood function. The log likelihood function is used to measure how well the current model parameter explain the observed data. It is computed as a log L of summation I is equal to 1 to n log of summation of k to k, k is equal to 1 to capital K pi k into normal distribution of xi given mu k, comma, this is the covariance. After each iteration, the EM algorithm, the log likelihood should increase, indicating improved the fitness. The EM algorithm stops iterating once the change in log likelihood becomes negligible, signaling convergence. Now the visualization, the visualization, this could be explained in terms of the graphs also. So the here, coming into the application. So in this we have to consider the main thing is the equation, and then this Gaussian distribution equation. This we are going to combine, and finally we are going to get the weighted sum of Gaussian. This is the main function of GMM. These are all the various parameters used in GMM and the steps involved in it. And the coming into the application, Gaussian mixture model are widely used in areas requiring clustering, density estimation, and in image segmentation. Pixels can be grouped based on color or identity. distribution. So suppose if you have 10 colors, various of 10 colors, first we will identify the primary colors, then we will be grouping into the colors. So in image segmentation, pixels can be grouped based on the color or intensity distributions. In speaker identification, voice features are modeled using GMM to distinguish speakers. GMMs are also effective for anomaly detection. Points falling in low probability regions are treated as outliers. Furthermore, they serve as building blocks in semi-supervised learning where some labels are missing and the model needs to infer group structure probabilistically. Next, advantages and limitations. The advantages of GMM are GMM offers several advantages over other clustering models. They allow soft clustering, which is more realistic in many scenarios. They can model elliptical clusters unlike k-means, which assume spherical shapes. Additionally, GMMs provide a probabilistic foundation which enables statistical inference. However, they come with limitations such as, even though it has got some advantages, it comes with some limitations also. They are coming with some limitations such as requiring number of components. Here only K, misplaced triple K, to be predefined. They are sensitive to the initial parameter settings and may converge to local rather than global maximum. They also involve more computational complexity compared to simpler models. Okay, coming into the summary, to summarize, Gaussian mixture models are flexible and powerful tool for modeling complex data distributions using multiple Gaussian components. The EM algorithm effectively estimates the model parameters by iteratively assigning probabilities and updating estimates. GMMs perform soft clustering and are well suited for real world problems where data distributions are not easily separable. Their ability to handle uncertainty and more overlapping clusters make them widely applicable in both supervised and unsupervised machine learning contexts. Hope everyone understood about the topic GMM. The remaining things we'll discuss in the next lecture. Thank you.